Hi, my name is Alejandro Flores Velasco, and I'll be talking about my paper for the European Symposium on Algorithms titled Coresets for the Nearest Neighbor Rule. This is a joint work with Professor Dave Mount from the University of Maryland, College Park. So first, let me give you a quick introduction to the problem of classification and to the nearest neighbor rule. We're given an initial training set T, which consists of n points in a given metric space. And in this metric space, we can define the distance between any 2 points. And we have some extra information about the points in P, which is that each of these points belong to one of a set of discrete classes that you can see as colors. And now the problem of classification is that if we're given a query point Q, which is unlabeled, we want to predict the class of this query point. And the nearest neighbor rule is one such classifier that predicts the class of that query point using the class of its nearest neighbor. Now, coresets, on the other hand, are defined as follows. If we're given some original data, a coreset is basically a subset of that data, such that answering a query exactly on the coreset gives us an approximation of the same query in the original data. And we'll say that this coreset is weak if it only works for certain queries and not all the possible queries. In this context, we define a coreset for the nearest neighbor rule as a subset of the training set, such that for any query point, its nearest neighbor in the reduced set is either of the same class as in the original set or the class of one of its approximate nearest neighbors. So first, let me give you a set of useful definitions that we're going to be using throughout the rest of the presentation. So if we're given a query point Q, we can obviously denote the nearest neighbor and the nearest neighbor distance. And we also say that 2 points are enemies if they belong to different classes. Similarly, we can also define the nearest enemy of any point in the training set along with its nearest enemy distance. Also, if we find the smallest nearest enemy distance in the training set, we define this to be the margin or gamma. Now, these definitions allows us to understand the complexity of the problem in question. And if we consider all the nearest enemy points of the blue points in the training set, which are these red points, and similarly we do the same with the rest of the classes, then we're left with a set of points which are the set of all nearest enemy points in the training set, which is of cardinality kappa. Additionally, if we consider the space partitioning of these points, and we consider the points that define the boundaries between classes, these are called border points. And there are tau number of such border points. And in particular, in the Euclidean case, we know that kappa is always less than or equal to tau. These two parameters are extremely important to understand the complexity of the boundaries between points of different classes. From here, we give you our main result, which is that we know there exists an epsilon coreset for the nearest neighbor rule, whose size is upper bounded in terms of kappa, gamma, and epsilon, and there's a dependency, an exponential dependency on the doubling dimension of the metric space. And this coreset can be computed in subquadratic time. And the rest of the presentation is going to be devoted to proving this result. There is, however, a similar problem to the one that we're trying to solve, which is called nearest neighbor condensation. And the idea with this problem is that we're also trying to reduce the training set, but we're only focusing on the effect that this reduction has on the original points in the training set. That is, the ones that we don't include in the subset. There are two main criteria used for condensation, and these are called consistency and selectiveness. And the basic idea is that we want, after reducing the training set, we want that for every point in the original training set, its nearest neighbor in the reduced set is closer than its nearest enemy in the reduced set. Selectiveness, on the other hand, is a little bit more strict, and we want that for any point in the original training set, its nearest neighbor in the reduced set is closer than its nearest enemy in the original set. So it's easy to see that selectiveness implies consistency. If we're given this initial training set as an example, this is an example of a minimum cardinality consistent subset, and this is an example of a minimum cardinality selective subset. And in general, the problem of nearest neighbor condensation involves finding ideally small consistent subsets. We can obviously define the corresponding optimization problems for finding minimum cardinality consistent and selective subsets, and both problems are known to be NP-hard. And additionally, most of the research has focused on proposing heuristics without any theoretical guarantees. Now, this is an outline for the state-of-the-art algorithms for condensation. So if we're given an initial training set as the one that we see in our left, FCNN and MSS were previously the two state-of-the-art algorithms for this problem, which run in quadratic time and behave really well in practice. However, they do not provide any guarantees on their size. On the other hand, we have the net algorithm, which also runs in quadratic time, but in practice is much lower, and it actually provides a tight approximation for the minimum cardinality consistent subset problem. However, as you can see, it does not do a good job at reducing the training set, and the authors provide an extra pruning technique, which they call net plus prune, which further reduces the training set, but still it does not compare to the reduction given by state-of-the-art algorithms like FCNN and MSS. More recently, we proposed two new algorithms called RSS and VSS, which also run in quadratic time and behave really good in practice. In the same paper, we show that we can upper bound these two algorithms, and we show that MSS, on the other hand, cannot be upper bounded, and for FCNN, it still remains open whether similar results could be achieved. In a more recent paper, we show that while FCNN cannot be upper bounded, there's a slight modification of the algorithm that can be upper bounded. So this is the state of the art on condensation algorithms, and we will build upon these algorithms in order to construct coresets for the nearest neighbor rule. So first, I'm going to talk about how we characterize these coresets, and in particular, we're focusing on how condensation affects classification when we consider approximate nearest neighbor searches. So if we're working with an initial training set and we're given a query point who's close to both its nearest neighbor and its nearest enemy, and on the other hand, we're given a query point whose nearest neighbor is far closer than its nearest enemy, we see that the first point is harder to correctly classify with epsilon approximate nearest neighbor queries than the second point, which is much easier to classify. This notion is formalized as the chromatic density of a query point, which you can see as the ratio between the nearest enemy distance and the nearest neighbor distance. And the idea here is that for any query point, if its chromatic density is greater than epsilon, that means that it's going to be correctly classified with epsilon approximate nearest neighbor queries. The problem is that even if the chromatic density of the query point before condensation was high, after condensation, the chromatic density can get reduced drastically. Thus, during condensation, we would like to keep some internal points such that we can guarantee that the query point is going to be correctly classified even with approximate nearest neighbor queries. Keeping this in mind, we extend the two criteria used for standard condensation and we call it alpha consistency and alpha selectiveness. And the idea here is that for any point in the training set, instead of considering the nearest enemy distance of the given point, we consider the shrink nearest enemy distance by 1 plus alpha, such that for any given point, the shrink ball is the one that is covered and not the original nearest enemy distance ball. And this implies that the chromatic density of any point in the training set is at least alpha. However, this guarantee is only valid for the original points in the training set, not for any given query point. However, we can extend this guarantee for any given query point as follows. So if the chromatic density after condensation gets smaller, we know that there's a function that depends on alpha and the original chromatic density that bounds the chromatic density after condensation. And this function is of the following form. So from this lemma that we prove in the paper, we can get two results. One result on weak corsets and one result on strong corsets. So the result on weak corsets is as follows. We know that any alpha consistent subset of P is a weak corset for the nearest neighbor rule for query points that have chromatic density greater than or equal to 2 over alpha. In our example, if this is our training set and we set alpha to be 0.1, the regions in yellow represent the query points that are correctly classified after condensation with alpha consistent subsets. And we see that when we increase alpha, these regions also increase. Now, our strong corset result is as follows. We know that any 2 over epsilon selected subset of P is an epsilon corset for the nearest neighborhood. And the way that we prove this is as follows. So we have two cases. The query points that had an initial chromatic density greater than or equal to epsilon, which were easier to classify. These query points we know that are going to be correctly classified after condensation. And on the other hand, query points that were hard to classify in the first place, that had chromatic density less than epsilon, these points are going to be classified with the class of any of its epsilon approximate nearest neighbors, therefore being a corset for the nearest neighborhood. So overall, we know that using standard condensation techniques, the chromatic density values of query points that are far away from the boundaries can get highly reduced. However, if we consider alpha consistent subsets, we can see that the chromatic density values are maintained in high enough values. Now, the next question is on how to compute these corsets, and we're going to present some results on the complexity and on efficient algorithms that find such subsets. If we consider alpha selective subsets, and in particular the corresponding optimization problem which finds minimum cardinality alpha selective subsets, we know that this is an NP-hard problem, and moreover, it's hard to approximate up to a factor of log n, and this result is an easy reduction from the dominating set problem. So if we have an initial graph that is the input for the dominating set problem, we make a copy of the graph and color the initial nodes as blue and the copy nodes as red. We connect each original node and with its corresponding copy, and we carefully assign the weights to those edges, finding a minimum cardinality alpha selective subset on the shortest path metric induced from this graph is the same as solving the dominating set problem. There's also an easy reduction from the alpha selective subset problem to the hidden set problem, and this implies that there is a polynomial time algorithm that has log n approximation factor in general metrics, and we'll call this approach alpha HSS. However, we provide a more practical algorithm for the problem, which is called alpha RSS, and this is an extension on the RSS algorithm that we proposed in previous works. The idea of this algorithm is a greedy selection of the points, in which we start with the points that are closer to the boundaries between classes, and then for every point, we're going to consider its nearest enemy ball, shrink by 1 plus alpha, and the idea is we want to cover this shrink ball, and we do the greedy selection based on whether this point was already covered or not. This algorithm runs in quadratic time. We can provide theoretical guarantees on its size, and it actually performs good in practice. This is the type of selection that this algorithm will make. This algorithm is actually an approximation of the minimum cardinality alpha consistent subset and alpha selective subset. And in particular, it computes a tight approximation of the min alpha CS problem, and it computes an approximation of the mean alpha SS problem up to this factor. And this, in particular, is a constant factor approximation for values of alpha that are lower bounded by a constant. More interestingly, for the proof of our main result, the size of alpha RSS is bounded by this factor. The way that we prove this is by a charging argument on every nearest enemy point in the training set, for which we consider the set of points whose nearest neighbor is that point P, and then we partition this set into a logarithmic number of subsets. And for every such subset, we know that the distance between any two points that were selected by the algorithm is lower bounded. And this allows us, by a simple Pacquiao argument, to upper bound the size of any of these subsets. And this yields a proof on the size of the selection of RSS. Finally, we show an alternative implementation of RSS that runs in subquadratic time. And the idea is as follows. There are two main bottlenecks of the algorithm. The first one is computing the nearest enemy distances of every point in the training set. And for this, we're going to use approximation in order to speed up the computation. The second bottleneck is during the greedy selection process of the points. And for this, we're going to use approximate nearest neighbor search techniques combined with static to dynamic transformations. Thus, we use approximate nearest neighbor search techniques as a black box in order to obtain the following time complexity result for an alternative implementation of alpha RSS. And this gives us the proof of our main result. So we know how to characterize any epsilon coreset for the nearest neighbor rule as 2 over epsilon selected subsets of B. We know that these subsets can be computed with alpha RSS, which is overbounded, and we know that we can compute it in subquadratic time using the alternative implementation of the algorithm. Additionally, we perform experimental trials to analyze the performance of these algorithms in practice. We use well-known benchmarks from the UCI machine learning repository that have up to 58,000 points in 64 dimensions, and we also generated some synthetic datasets with up to 100,000 points. And then we run the algorithms on these benchmarks in order to analyze its performance. Apart from RSS, we also compare other algorithms. One of these algorithms is alpha HSS, which is the algorithm based on the hidden set reduction. And additionally, we extend the net FCNN and SFCNN algorithms in order to compute alpha selective subsets and alpha consistent subsets. We first compare the algorithms in terms of the size of the selected subsets. And we see that while we increase the alpha parameter, obviously the size of the subsets increases, but the size of the selected subsets by most of the algorithms is comparable except for AlphaNet. However, the difference becomes more apparent in terms of the runtime of the algorithms. We see that the hidden set reduction algorithm is much lower than the rest of the algorithms, and we see that alpha RSS outperforms all the other algorithms, especially when alpha is increased. Keep in mind that the implementation used for alpha RSS is the quadratic time implementation. We also implemented the subquadratic version of the alpha RSS algorithm and experimented on how the epsilon parameter used for the approximation computation can affect the size of the selected subset and the time that it takes to compute this subset. And we see that evidently, while increasing the epsilon parameter increases the size of the subset, the runtime of the algorithm gets reduced. And this behavior is independent on the value of alpha that we use. Thank you so much.